Hi everyone, this is Saikat Dey. I am a second year PhD student at Systems Engineering Department in Arizona State University in Mesa, USA. Today I'll be taking you through this presentation concerning our collaborative work to facilitate energy usage to some of the underserved off-grid communities in USA, which is also our official entry to the Help Others program conducted by the IEEE Industrial Electronics Society. The title of the work is Multiport, Multi-directional, Modular and Scalable Power Conversion Platform with DC-AC source/storage integration. This is a collaborative work between a team from Arizona State University and Higher Art Incorporated. I will start with providing a brief background of our ongoing project, its motivation, and expected outcomes. It is to be noted that this project is funded by the US Department of Energy through its Small Business and Business Innovation Research Program and is managed by Dr. Stan Atsti from Sandia National Labs. The major motivation behind this project is to innovate technologies that will make renewable energy generation, storage, and its integration more sustainable and accessible. Through this project, we aim to develop an adaptable and deployable power conversion system for energy storage and to provide sustainable power solutions for disadvantaged off-grid communities. The expected outcome of the project highlights a power conversion system with significant increase in scalability, adaptability, while sensing and connecting various renewable technologies with the storage, and decrease in system cost and size compared to the traditional off-grid power conversion designs. In order to turn this project into a reality, we have formed a well-balanced and technically equipped team. The ASU side of the team is majorly formed by my PhD advisor, Professor Ayan Malik, Professor Kanan, and myself. Professor Malik is taking the charge of top-level power electronic architecture design and optimization. Alongside him, I am taking care of the multi-port power converter design, prototyping, and testing while formulating the loss optimal control strategies. Further, Professor Kanan, with his more than 20 years of expertise in the energy storage research, joins us in the battery modeling and phase change-based thermal management design. In this project, we are collaborating with Trevor, who is the founder of Higher Art Incorporated, in order to facilitate the power conversion system installation on site and commercializing the product under development. Moving forward, this slide identifies the major problem statement of the project from the power electronic implementation point of view and how we are trying to reach the possible solutions to the problem. In short, the primary objective of this work is to design a power converter integrating multiple DC and AC sources or loads with a multiple directional power flow capability. Investigating the existing literature, the traditional approach to meet the desired goal is identified, where multiple DC-DC or DC-AC converters are employed in cascaded manner that integrates each of the DC or AC power sources or sinks with a common stiff DC link. One of the major drawbacks in such a design is a higher number of components due to individual DC-DC or DC-AC stages, which incurs higher losses, increased system cost, and lower efficiency. However, such an architecture is easy to control due to the availability of the stiff DC link and discrete converter controller. On the other hand, a more recent and cost and loss efficient design is shown in the right side of the slide, where a multi-port converter is designed to integrate the available DC-AC power sources and sinks using a multi-winding transformer and their respective active edge bridge cells. Such a design leads to a less active components under use and better system efficiency. However, designing and efficiently controlling a multi-active bridge converter can be technically challenging due to its coupled power flow between the connected ports. Due to its architectural advantage and cost effectiveness, we have chosen the MAV converter as our potential solution, and we have tried to encounter its implementational challenges with innovative solutions. As mentioned in the previous slide, The primary challenge in the multi-active bridge converter is its coupled nature of power flow. In any dual-active bridge derived topology, such as MAB, the power flow between two of the ports is controlled by the phase difference between the respective edge bridge waveforms. When multiple ports are actively taking part in the power transfer, the total power sourced or synced by any of the ports is determined by the phase shifts of each of the active bridges, and not only by that particular port's phase shift. This results in a poor voltage regulation performance if simple PI controllers are implemented to control the power flow. To cater this issue, we have proposed a decoupled control strategy through which a MIMO control loop can be separated into multiple independently controlled CISO control loops for easier and robust controller implementation. Secondly, another identified drawback in the MAB converter is its poor efficiency at light load and non-unity normalized gain conditions due to the increased transformer winding RMS currents and loss of ZVS. Such a problem is addressed by our proposed hybrid optimal phase duty control, where duty cycle variables of the individual edge bridges are also optimally employed alongside the existing phase shift control to reduce the conduction as well as switching losses in the active devices. Furthermore, we have put an extensive effort to integrate the required line inductances of the MAB converter within the transformer in the form of leakage inductances in order to further reduce the system size. The details of the converter design, the practical value propositions through this work are summarized in this slide. The multi-port integrated design of this architecture brings in a cost saving of up to 40%. The smaller converter footprint reduces the weight and the volume of the converter by 20 and 25% respectively, compared to the multi-stage design. The higher efficiency of the converter utilizing optimal phase duty control can attain higher energy savings in a yearly basis. Moreover, due to the adaptable topology, such converter is scalable up to more than 10 kilowatts and also integrable with 120 volt as well as 240 volt 50 to 60 hertz frequency grid fault. Implementation and details of this converter is showcased in this slide. Where you can see it is a triple active bridge converter where block 1, block 2 and block 3 are showcasing three different active bridges which are connected or coupled together using one multi-active bridge multi-winding transformer having a transistor of N1, N2 and N3, having a leakage inductance of L1, L2 and L3. The block 1 is connected with the PV side. The block 2 is connected with the grid side, and block 3 is connected with the battery side. And the PV side has a nominal input voltage of 40 to 60 volts. The battery side is having a nominal output voltage of 28 volts. It can vary from 16 to 28, and the AC side grid voltage can vary from 120 volt RMS to 240 volt RMS. This slide showcases the proposed circuit topology, where you can see three active bridges formed by four MOSFETs or four active semiconductors, and we can achieve one switching node for switching voltages V1, V2, and V3 across each of the bridge outputs, and those output voltages are connected across the three winding transformer. And we can have a power flow in between each of the bridges by changing the phase shift between these voltage levels V1, V2 and V3. Also, we can integrate the duty cycle variables in each of the bridge voltages V1, V2, V3 in order to facilitate the more efficient power flow by controlling the RMS winding currents and the peak currents. There are a few innovative approaches that we have taken in this converter implementation. Those we'll be talking about in later slides. PV system during the non-unity output voltage gain and light load operation. With this purpose, we first obtain the correlation of the conduction loss with the phase duty control variables by formulating the PV circuit current RMSs as a function of the control variables. Then, to find out the optimal hybrid phase duty controller operating point, a multi-variable, multi-constant loss optimization problem is found and solved. Proposed multivariable control PWM modulation ensures the lower RMS currents in the TEV windings for any power demand, which is shown in the middle plot. Similar to the conduction loss, an effort is made in our work to optimize the switching loss of the system. With this intent, the total switching loss of the converter is formulated as an equivalent objective function, summing up the peak winding currents during the hard switching transients. ZVS conditions for all the active bridges are also identified and incorporated in the switching loss equivalent model as shown in the flowchart. Then we have identified the optimal phase duty variables for a wide gain and load operation range by optimizing the formulated objective function that ensures the ZVS maximization while reducing the overall losses in the switching network. Both of these works are published in recent IEEE transactions. Another key component in our technology innovations is the controllable leakage integrated three-winding transformer design for the TAV converter that circumvents the requirement of bulky external line inductors. We have proposed one asymmetric winding arrangement in the E-shaped transformer core that forms a leakage flux path through the central limb of the core. Such interleaf design help us achieving higher leakage inductance while maintaining high LM requirement for the TAV power flow. Lastly, in order to decouple the power flow loops in the TAV converter, a generalized harmonic approximated decoupler network is proposed and implemented in this work that truly decouples the power loops in a TAV converter. More than that, it enables the implementation of the independent PI controllers to regulate the output power flow by controlling some CISO systems. This slide presents the simulation results from our triple active bridge converter. Uh, this converter is simulated at 2 kilowatt of power conversion happening from input PV side to which is supplying to the grid at 1 kilowatt of power, as well as supplying the battery 1 kilowatt of power at 28 volts, and the grid is at 120 volt AC RMS at 60 Hz frequency. You can see in the right hand side zoomed in waveform, the bridge voltages and the winding currents are shown here. You can see there is a clear phase shift between the block 1 bridge and block 2 and block 3 bridges identified as phi 2 and phi 3. So the phi 2 and phi 3 are the phase shifts of the secondary and tertiary block or the edge bridges. And this phase shift is determining how much power is being flown from the primary side to the secondary and tertiary side. On the left hand side figure, you can see the grid side AC voltage reference and the output voltage are following each other, as well as the PV, as well as the grid power is sinusoidally varying to a frequency with average of 1 kilowatt. For this project, we have fabricated two converters. The first one is one lower power DC to AC microinverter, which is a power level of 500 watts. The different parts of the converter is identified and marked in this slide. You can see in the input side we have DC link capacitors. Following it, we have a primary side high frequency edge bridge from using EPC GaN devices having 100 volts voltage stress, maximum voltage stress. And then we have the leakage integrated planar transformer. Following that, we have the secondary side high frequency bridge formed by the 650 volts GaN system GaN devices. And after that, we have the unfolded stage formed by the SIG devices. And following that, we have the EMI filter, and then we have the grid side AC output. It can be set at 120 volt AC as well as 230 volt AC. And to facilitate the power flow, we have the controller, the TMS 320 F series microcontroller by TIDSP. And this design is targeted to reach an efficiency of 96% and above. The second or the final converter prototype that we have under study is the DC AC DC TAB triple active bridge converter, and now we have the input side PV, which can regulate our voltage at 40 to 60 volts. That is the PV side marked with the red color. The green color marks the battery side output or the input, that is regulating voltage at 16 to 28 volts. And the green marking shows the AC grid side output port. It can be having 120 volt AC or 230 volt AC. And the EMI filter is situated in a separate board. All the other details of the circuit parameters are shown in the table.
Hi everyone, we are at Peace Lab at Arizona State University, and this is the experimental setup for the multi-directional multi-port DC-DC AC converter platform, employing one triple active bridge topology. And this converter can integrate the grid side and the renewable energy generation side, maybe PV or the wind, as well as it can integrate the energy storage system or the battery all together. So these three together can be employed in this system, can be connected. So there is a 3-winding transformer. It is in the behind. You can see the 3-winding transformer. The three ports are coming here, and we have 3 active bridges which are connected to this transformer. One is under this heatsink, another one is this heatsink, and another one is here. And this is the primary side edge bridge. We can find a PV side input connected here. The voltage can be rated from 40 volt to 60 volts, as well as to 80 volts. The devices are rated for 80 volts. Those are EPC GaN devices, 2 in parallel. And this one is the second bridge, or you can say the battery side bridge. The battery voltage, the output voltage is 28 volt nominal, but it can vary in a wide range from 16 to 28 volts. We have also parallel devices underneath them, 60 volts GaN devices from APC. And the third, or the tertiary bridge, is actually the bridge that is connected to the grid side. And we have GaN systems, GaN devices here, forming one edge bridge. And the DC link, or the high frequency DC link, in fact, that is a rectified DC link, that is across this bridge, as well as this bridge. This is the unfolder stage. We have silicon carbide devices here. This is a 50 hertz. This has a 50 hertz switching frequency. This is unfolding the AC rectified sine wave, so that we can find a AC signal at the output. This is the EMI filter. This is the EMI stage, and the line frequency inductor we have here. And then this can go to this loads. So we have 2 loads connected here, one here and one here. And then right now this is one source and 2 output systems. We can modify this setup as 2 input and 1 output system, like the PV and the battery are sourcing power to the grid, as well as we can set up it like the grid is feeding power to the battery, and vice versa. We will investigate 2 of the experimental modes, where the PV will be charging the battery, and the second one will be the PV will be sourcing power to the grid. For the first part of the experiment, we have connected one DC power source with the input side, emulating the PV input at 40 volts. And we are expecting 28 volts at the output of the secondary side. This converter is controlling this operation is being controlled in closed loop by this digital controller. We are using TI-DSP for this. And I have ran the code here. So right now the converter is running. I'll be turning on the power source. So right now you can see we have got, so The channel 1 is the primary side bridge switching waveform, and the channel 2 or the blue waveform is the secondary side bridge switching node waveform, and there is a phase difference in between these two nodes, these two channels, and that only determines the power that is flowing from primary side to the secondary side. You can observe that the primary is sitting at the DC link is sitting at 40 volts nominal, and the secondary side is sitting at around 28 volts nominal, which is expected. And also another thing is to note is that this converter is controlled by phase modulation, only phase modulation, where there is a clear phase difference between the primary side switching node voltage and secondary side switching node voltage, but there is no duty control of each of the bridge voltages, so the duty is 0 here. We can observe an inductor current of around 10.64 ampere RMS.
This slide presents the result from our first experiment, where the 40 volt PV side is supplying power to the 28 volt battery side when the grid side is disconnected. The this type of power conversion is happening because of the phase shift modulation, where duty cycle modulation is not involved. Although with the involvement of duty cycle modulation, we can observe a lower RMS current than what we can observe in this slide.
For the second part of the experiment, where the PV will be sourcing power to the grid side, we have connected a DC power source at 40 volt and 40 to 60 volt nominal at the input side DC link, and we are expecting 115 volt AC RMS at 60 hertz signal at the output side from the EMI filter. For this type of power conversion, we have a dual active bridge type of topology at the first stage, and that is followed by an unfolder stage formed by this edge bridge. That is a low frequency edge bridge having 60 hertz frequency, and this is the high frequency edge bridge forming the secondary side of the dual active bridge converter. And this is the primary side of the dual active bridge converter, and the DC link that will be formed after the secondary side, that is of a rectified sine wave structure, and this unfolding stage is unfolding that and forming a pure sine wave at the extreme output. All the controls are happening using this TIDSP, and it is sensing the output voltage, and it is trying to follow a reference voltage setup from the inside. And more than that, we are trying to implement the duty cycle control as well as phase shift control in order to efficiently flow the power from the input side to the output side by reducing the total conduction loss as well as by achieving ZVS during the power conversion.
The DC-AC operational experimental result is shown in this slide. From where the PV side at 40 volts is supplying power to the grid side at 120 volt AC RMS. The left hand side waveform shows the input and output voltages from the converter. As you can see, the PV side is situated at 40 volt DC voltage, and the grid side output voltage is 120 volt AC. The peak reaching around 169 volts. It is having a resistive load, so the IG is following the PG, and the PG is having a 2F frequency ripple, and it is the maximum power is almost reaching 400 watts because the average power is at 200 watts. The right hand side image shows the switching node waveforms, where the V1 is the primary side bridge voltage, and the V2 is the secondary side bridge voltage, and the I1 is the transformer winding current from the primary side. We will see two of the zoomed in waveform, one slice taken at the high line of the AC voltage, and one slice taken at the low line of the AC voltage, and we will zoom in and see the switching waveform in the next slide. Before that, we have done the THD analysis also of the output voltage, and we have found around 10% of THD with this only phase shift modulated power conversion. That's when we need to know, we need to understand, we need to implement the higher order or phase shift modulations along with the duty cycle variable into the control, so that we can achieve a lower unity gain or near zero gain also in this kind of power conversion mode. In this zoomed in waveform of the input and output bridge voltages and winding currents, we can observe a substantial phase difference between the primary and the secondary side bridge voltages. This phase shift determines the power that is flowing from the PV side to the grid side, and during this high AC line power operation, this power is maximum, which is reflected in the phase shift phi 2. Also, the primary winding current RMS is at 11 amperes due to its higher power due to this higher power transfer. In the second zoomed in waveform taken at low AC line, we can observe a zero phase shift between the primary and the secondary bridge voltages. This is due to the requirement of zero power transfer at this zone. Although we intend to reach zero voltage at the secondary side during this operation, due to the phase modulated control, it is not possible to achieve, and we reach 15 volts at the secondary instead. Although the primary winding current RMS is high at 7.5 ampere due to the extreme gain operation, although we intend to transfer no power during this step. Here, the introduction of the duty cycle variable control can bring in an efficiency benefit of 3.4% by reducing the RMS currents by 23%, which is proven in our prototype. The technical contributions of our work is summarized here in the slide. Firstly, the duty cycle control along with the phase shift control optimizes the system conduction as well as switching losses by providing higher degrees of freedom to the triple active bridge converter controller. Secondly, the proposed decoupled control of the TAV ports decouples the power flow loops while enabling online maximum efficiency tracking. Thirdly, the experimental and the simulation results verify the theoretical models of the RMS current calculations and the power flow regulations under the proposed TAV control scheme. Fourthly, the leakage integrated interleave design of the three-winding transformer helps reducing the total system size and losses. Owing to the technical innovations of our multi-port converter that integrates the renewable energy resources with the energy storage systems and the localized grid, it has substantial impact on the targeted off-grid communities at an economical as well as societal level. A study done by the National Renewable Energy Laboratory or NRL suggests that the low to moderate income or LMI communities constitute 43% of all the households in USA. However, only 15% of them are solar adapters. This number is projected to increase by 50% over the next 10 years if residential PV system cost can be minimized by 13% or below. From this economical aspect, our proposed solution of multi-port DC-DC AC converter has a significant role to play, as our solution can reduce the system cost by 40%, while being a useful alternative for the cascaded multi-staged power conversion architectures. With such cost reduction, implementation of this can lead to a 14% savings when modeled for an average LMI residential solar install. This will spur increased demand in similar fashion to the NREL model without requiring additional government spending. Owing to the technical innovations of our multi-port converter that integrates the renewable energy resources with the energy storage systems and the localized grid, it has substantial impact on the targeted off-grid communities at an economical as well as societal level. A study done by the National Renewable Energy Laboratory or NRL suggests that the low to moderate income or LMI communities constitute 43% of all the households in USA. However, only 15% of them are solar adapters. This number is projected to increase by 50% over the next 10 years if residential PV system cost can be minimized by 13% or below. From this economical aspect, our proposed solution of multi-port DC-DC AC converter has a significant role to play, as our solution can reduce the system cost by 40%, while being a useful alternative for the cascaded multi-staged power conversion architectures. With such cost reduction, Implementation of this can lead to a 14% savings when modeled for an average LMI residential solar install. This will spur increased demand in similar fashion to the NREL model without requiring additional government spending. Owing to the technical innovations of our multi-port converter that integrates the renewable energy resources with the energy storage systems and the localized grid, it has substantial impact on the targeted off-grid communities at an economical as well as societal level. A study done by the National Renewable Energy Laboratory or NRL suggests that the low to moderate income or LMI communities constitute 43% of all the households in USA. However, only 15% of them are solar adapters. This number is projected to increase by 50% over the next 10 years if residential PV system cost can be minimized by 13% or below. From this economical aspect, our proposed solution of multi-port DC-DC AC converter has a significant role to play as our solution can reduce the system cost by 40% while being an useful alternative for the cascaded multi-staged power conversion architectures. With such cost reduction, implementation of this can lead to a 14% savings when modeled for an average LMI residential solar install. This will spur increased demand in similar fashion to the NREL model without requiring additional government spending. Looking at the community impact of our integrated power conversion system solution, we intend to commercialize it as a product. Having said that, there will be future versions of the prototype under study to be developed. In the current stage, with the proof of concept PV converter, the loss optimal multivariable phase duty control is verified. The thermal performance and the protection features of the circuit is under testing at this point. The future steps for moving towards to a beta prototype from this alpha prototype are highlighted in this slide. We intend to design and integrate the auxiliary power supply and on-chip digital control in the future converter board. Also, a vigorous reliability assessment, startup sequencing, mechanical enclosure design, etc. are the major identified future steps. Looking at the community impact of our integrated power conversion system solution, we intend to commercialize it as a product. Having said that, there will be future versions of the prototype under study to be developed. In the current stage, with the proof of concept PV converter, the loss optimal multivariable phase duty control is verified. The thermal performance and the protection features of the circuit is under testing at this point. The future steps for moving towards to a beta prototype from this alpha prototype are highlighted in this slide. We intend to design and integrate the auxiliary power supply and on-chip digital control in the future converter board. Also, a vigorous reliability assessment, startup sequencing, mechanical enclosure design, etc. are the major identified future steps. In future, with the phase 2 of this project, we plan to commercialize our product targeting the microgrid and the commercial market. From the sales front, we will license our technology with a reputed manufacturer rather than manufacturing ourselves due to the lack of manufacturing capability within an academic environment. Our limited customer survey suggests that the reliability of such product will be more crucial than the cost itself. That is why the reliability assessment of our prototype is the key step moving forward. This is our potential roadmap towards commercializing this product. Presently, we are in the process of submitting the phase 1 of this project proposal to DOE. By the quarter 2 of 2023, we project to start the build testing of the product. If everything falls in place, we expect to observe the product launching in the market by 2025. Presently, we are in the process of submitting the phase 2 of this project proposal to DOE. By the quarter 2 of 2023, we project to start the beta prototype development, and by quarter 4 of the same year, the pilot programs will be identified. Following that, a potential production partner needs to be identified, and we can start the field testing of the product thereafter. If everything falls in place, we expect to observe the product launching in the market by 2025. This is our potential roadmap towards commercializing this product. Presently, we are in the process of submitting the phase 2 of this project proposal to DOE. By the quarter 2 of 2023, we project to start the beta prototype development, and by quarter 4 of the same year, the pilot programs will be identified. Following that, a potential production partner needs to be identified, and we can start the field testing of the product thereafter. If everything falls in place, we expect to observe the product launching in the market by 2025. With this, I would like to thank our collaborators, Dr. Kannan from Arizona State University, Trevor from HireWire, and Dr. Stan from Sandia National Labs. Also, I would love to mention our sponsor, the US Department of Energy, for financially supporting us during this project tenure. I would like to conclude my presentation by showing off the developed working converter prototypes and one of our poster that we had presented during the DOE Office of Electricity Energy Storage peer review meeting, happened in October this year. Lastly, we have a long way to go with the dream of providing the access of sustainable energy to the whole mankind. Thank you.